being the voices of nature for a greener future, delivering nothing but the truth. This is Dzes 143 in your radio dial. Stay in the know by being environmentally know. Now broadcasting live from home in collaboration with the BSES Newsroom Manila, good afternoon. Wishing you all a pleasant day as it is very sunny here in Manila, November 16, 2022. I am 𝔼ℕ𝕍𝕀ℝ𝕆ℕ𝕄𝔼ℕ, your local DZES 143 host and resident environmentalist, serving you the hottest and most leading environmental news of the day so we could all stay in the know by being environmentally know. So for today's headliner and special coverage, we will be talking everything there is to know about water treatment. Reported just this morning, thousands of fish turn up dead in Las Piñas and 𝔼ℕ𝕍𝕀 shores due to polluted waters. Initial water tests taken from the two cities revealed low levels of dissolved oxygen as well as other abnormalities according to the Bureau of Fisheries and Aquatic Resources or BFAR. As we wait for further updates on this alarming issue, let us first relate this on the importance of water treatment. And of course, as this is a broad topic, I would need more professional input on this matter. So, our program proudly introduces three of the most prominent and professional guests and environmental advocates of the country. So, let us all welcome Ms. 𝔼ℕ𝕍𝕀, Sanitary Engineer of the Muntinlupa Water Treatment Plant. Mr. John Paul Estrella, Manager of the Manila Water Company. And Mr. 𝔼ℕ𝕍𝕀 Gugolin, Water Treatment Specialist of the Maynilad Water Services Incorporated. Welcome to our guests. Now to start off our discussion, we all know how water is important to everything on earth. It is the lifeline of basically every living being, and especially to humans since we have found numerous ways on how to make efficient use of it. But as time passed, we have also contributed to the degradation of its quality. This justifies the necessity of water treatment or water disinfection. The treatment of water can be divided into three major categories. The first is the purification for domestic use, the second is the treatment for specialized industrial applications, and the third is treatment of wastewater to make it acceptable for release or reuse. The type and treatment degree are strongly dependent upon the source and intended use of water. As world demand for limited water resources grows, more sophisticated and extreme and extensive means will have to be employed to treat water. And of course, most physical and chemical processes used to treat water involve similar phenomena, regardless of their application to the three main categories of water treatment that will be mentioned later. Therefore, after introductions to water treatment for municipal, industrial use, and disposal, each major kind of treatment process is discussed as it applies to all of these applications. Now, to help us understand municipal water treatment, here's Engineer Garcia to enlighten us on this process. Engineer?
Hello, good day, Miss Isa, and hello to everyone listening today.
Good day, Miss Engineer. Now, before we dive in, Engineer, can you tell us about what is municipal water treatment and how does it work?
So, Miss Isa, first of all, the municipal water treatment, it performs the wonder with the water fed to it. As some of us doesn't know that the clear, safe, and even tasteful water, it comes from our faucets that may have started as murky liquid pumped from a polluted river. It can have mud and even swarming bacteria. Or either its source may have been well water or groundwater, which is much too hard for domestic use. it contains high level of stain-producing dissolved iron and manganese. So the operator's job in water treatment plant is to make sure that the water um, comes from it presents no hazards or harmful effects to the consumer. Aside from that, for its function, let's start with the raw water taken from wells or groundwater that will go to the aerator, where water will have a contact with air, which it removes volatile solutes such as hydrogen sulfide, carbon dioxide, methane, and even volatile odorous substances such as methane thiol and bacterial metabolites. With that, this can also help in iron removal by oxidizing soluble iron 2 to insoluble iron 3. So the second step is the addition of lime, where it can be calcium oxide or calcium hydroxide. After aeration, that raises the pH and creates the formation of precipitates, which are the hardness ions of calcium ion and magnesium ion that settle from the water in a primary basin. The solid material remains in suspension and requires the addition of coagulants, and that would be the third step. It settles the colloidal particles. The activated silica or synthetic polyelectrolyte can be added to stimulate coagulation and flocculation. The addition of carbon dioxide to lower the pH. After that, the settling occurs in secondary basin. After that, sludge from both the primary and secondary basins are pumped to the sludge lagoon. And finally, the water is chlorinated, filtered, and pumped to the city water mains. And that's it, Miss Isa.
Very informative, Miss Engineer. Now, how about the treatment of water for industrial use? Let's say what are the factors needed if you would consider operating an industrial water treatment facility, for example.
So, Miss Isa, there are major industrial uses. I can include here the boiler feed water and the cooling water. For example, the cooling water may require only minimal treatment. However, the removal of corrosive substances and scale-forming solutes is essential for boiler feed water. Take note that the water used in food processing must be free of pathogens and toxic substances. Thus, improper treatment of water for industrial use can cause several problems. It could be corrosion, scale formation, reduced heat transfer in heat exchangers may occur, as well as the reduction of water flow, and product contamination may also occur as well. These effects may cause equipment failure, increased energy due to inefficient heat utilization or cooling, increased costs for pumping water, and product deterioration. And we have numerous factors also to consider in designing and operating industrial water treatment facility. So this includes the following, which are the water requirement, quantity and quality of available water sources, as well as the sequential use of water. This refers to the successive uses for applications requiring progressively lower water quality. We also include the water recycle, and lastly the discharge standards.
Another question, ma'am. Are there any types of treating water for industrial use?
So for your question, Miss Isa, in types of treating water for industrial use, we have the external treatment and the internal treatment. So for the external treatment, it is usually applied to the plant's entire water supply. It uses processes such as aeration, filtration, and even clarification to remove material that might cause problems from water. This basic treatment, the water can be divided into streams or some to be used without further treatment, and the rest to be treated for specific applications. While, on the other hand, the internal treatment is modifying the properties of water for specific applications. Um, the examples of internal treatment could be first, the reaction of dissolved oxygen with hydrazine or sulfide. Second is the addition of chelating agents to react with dissolved calcium ions and prevent formation of calcium deposits. Third is the addition of precipitants such as phosphate used for calcium removal. Fourth is the treatment with dispersants to inhibit scale. Fifth, the addition of inhibitors to prevent corrosion. And the sixth, we also include here the adjustment of pH. And lastly, the disinfection for food processing uses or to prevent bacterial growth in cooling water. And that is all for today, Miss Isa. Thank you for having me here and have a good day.
Thank you so much, Ms. Garcia. Once again, Ms. J.𝕑𝕬 Garcia, the sanitary engineer of the Muntinlupa Water Treatment Plant. Now, as we move on to the next topic, may I call on Mr. Estrella for sewage treatment? Mr. Estrella?
Good day to you too, Miss Isa, and thank you for the invite.
Mr. Estrella, as the present Manila Water Company manager, can you share to us what's your knowledge about sewage treatment?
Sure. So, sewage is also wastewater, but it contains contaminated water from homes, schools, and businesses. So basically, it comes from toilets, showers, dishwashers, and many more. Typical municipal sewage contains oxygen-demanding materials, sediments, grease, oil, scum, pathogenic bacteria, viruses, pesticides, and many more that is very toxic and has chemicals. And it is the job of the wastewater treatment plant to remove as much as possible all of these contaminants. The current process for the treatment of wastewater can be divided into three main categories: the primary treatment, the secondary treatment, and the tertiary treatment.
Mr. Estrella, you've mentioned three categories involved in sewage treatment. Can you explain each of those?
Yes, so in primary waste treatment, it consists of the removal of insoluble matter such as grit, grease, and scum from water. The first step is basically screening. So the purpose of screening is to remove or reduce the size of trash and large solids that get into the sewage system. Next is the grit removal. Grit is basically materials that are like sand and coffee grounds that do not decompose very well and has a very high settling velocity. So grit removal is practiced to prevent its accumulation in other parts of the treatment system, to reduce clogging of pipes and other parts, and to protect moving parts from abrasion and wear. So grit is normally allowed to settle in tank under conditions of low flow velocity. Then it is scraped mechanically from bottom of the tank. Then the last part or last stage is the primary sedimentation. So it removes both settleable and floatable solids. So example of these are um, greases, which consist of oils, waxes, free fatty acids, and insoluble soaps that contain some chemicals. Normally, some of these greases settle with a sludge and some floats to the surface where it can be removed by skimming device. The next is secondary waste treatment, which is designed to remove BOD or biochemical oxygen demand, which is usually by taking advantage of the same kind of biological processes that would otherwise consume oxygen in water receiving the wastewater. The secondary treatment by biological processes takes many forms, but mainly is the action of microorganisms provided with added oxygen degrading organic material in solution or in suspension until the BOD of the waste water has been reduced to acceptable levels. The first stage or one of the simplest biological waste treatment processes is the trickling filter, which where the wastewater is sprayed over rocks or other solid support material covered with microorganisms. The structure of the trickling filter is such that the contact of the wastewater with the air is allowed and degradation of organic matter occurs by the action of the microorganisms. Next is the rotating biological reactors or contactors. It is another type of treatment system consists of a group of large plastic discs mounted close together on a rotating shaft. The device is positioned horizontally such as that any particular instant half of each disc is immersed in water and the other half is exposed to air. The shaft rotates constantly so that the submerged portion of the disc is always changing. The disc is usually made of high-density polyethylene or polystyrene and accumulate thin layers of attached biomass, which degrades organic matter in the sewage. The last is the activated sludge process. In the activated sludge process, the most versatile and effective of all wastewater treatment processes, the microorganisms in the aeration tank convert organic material in wastewater to microbial biomass and CO2 or carbon dioxide. The oxygen nitrogen is converted into ammonium ion or nitrate, and the organic phosphorus is converted to orthophosphate during this process. The activated sludge process provides two pathways for the removal of the BOD or biochemical oxygen demand. First, it can be removed by oxidation of organic matter to provide energy for the metabolic processes of the microorganisms, and the second is synthesis, incorporation of the organic matter into cell mass. In the first pathway, the carbon is removed in the gaseous form as CO2, and in the second pathway, it provides for the removal of carbon in solid in biomass. The dewatered sludge can be incinerated or used as landfill. The last part is the tertiary waste treatment, or sometimes called advanced wastewater treatment. Unpleasant as that may be, many people drink used water, that has been discharged from a municipal sewage treatment plant or from some industrial process. This raises serious questions about the presence of pathogenic organisms or toxic substances in such water. So obviously, there is a great need to treat wastewater in a manner that makes it amenable to reuse. This requires treatment beyond the secondary processes. So the tertiary waste treatment is used to describe a variety of processes performed on the effluent form secondary waste treatment. The contaminants removed by the tertiary waste treatment fall into the general categories of 1. The suspended solids, 2. Dissolved organic compounds, 3. The dissolved organic materials, including the important class of algal nutrients. In addition to these chemical contaminants, secondary sewage effluent often contains a number of disease-causing microorganisms requiring disinfection in cases where humans may later come in contact with the water. Among the bacteria may be found in secondary sewage effluent organisms causing tuberculosis, dysenteric bacteria, cholera bacteria, and bacteria causing typhoid fever and bacteria causing mad fever. In addition, viruses also can be found in these contaminants and causing diarrhea, eye infections, infectious hepatitis, and polio may be encountered. That is all, Miss Isabel.
Thank you so much, Miss Australia, for that very educational talk. I hope our audience indeed got educated. Once again, Mr. John Paul Australia, Manager of the Manila Water Company, Incorporated. I hope you all are still interested in our next topic, which is industrial wastewater treatment, that will be discussed by Mr. Gogolin. Good afternoon, Mr. Gogolin.
Good afternoon, Miss Isa, and good day, everyone.
Mr. Specialist, as one of the people responsible for ensuring that industrial wastewater should not be contaminated enough to degrade the national water systems, can you tell us, Mr. Gogolin, your knowledge of industrial wastewater treatment?
Well, industrial wastewater treatment involves numerous biological, chemical, and physical processes. However, these processes are applied not only to industrial wastewater but also during treatment of water for municipal and industrial use, as well as for treating sewage. The content of water is always varying. Indeed, it contains different materials or substances that may be dissolved or not. Hence, different techniques or processes are done to remove such materials or substances from water.
Mr. Specialist, as one of the people responsible for ensuring that industrial wastewater should not be contaminated enough to degrade natural water systems, can you tell your knowledge on industrial wastewater
Well,
treatment?
these processes are involved in removal of different types of substances. So, let me discuss each of those. First, for the removal of solids, relatively large solid particles are removed from water by simply settling and filtration, whereas the removal of colloidal solids from water usually requires coagulation. Salts of aluminum and iron are the coagulants most often used in water treatment. Of this, alum is most commonly used. For removing flocculating particles, natural and synthetic polyelectrolytes are used, such as starch and cellulose derivatives, proteinaceous materials, and gums composed of polysaccharides. Next, for the removal of calcium and other metals, it involves several processes used for softening water. For example, the lime soda process, which involves the treatment of water with lime or calcium hydroxide and soda ash or sodium carbonate. In this process, calcium is precipitated as calcium carbonate and magnesium as magnesium hydroxide. In addition, calcium can be removed from water very efficiently by the addition of orthophosphate. Further, water can be purified by ion exchange, which is the reversible transfer of ions between aquatic solution and a solid material capable of bonding ions. The removal of calcium and magnesium ions from solution by the cation exchange reaction is a good illustration of the process. First, the water is passed over a solid cation exchanger in the hydrogen form. As a result, the cations in solution are replaced by hydrogen ions, yielding water as the sole product. Moreover, chelation is an effective method of softening water without actually having to remove calcium and magnesium from the solution. For example, um, chelating calcium ion with excess anion reduces the concentration of hydrated calcium ion. Um, Polyphosphate salts and NTA are chelating agents commonly used for water softening. Next, for the removal of iron, manganese, and heavy metals, the basic method depends upon oxidation to higher insoluble oxidation states, wherein chlorine and potassium permanganate are commonly employed as oxidizing agents for iron and magnesium. Differently, lime treatment is a way for precipitation of heavy metals such as mercury, cadmium, and lead as insoluble hydroxides or basic salts. However, this process does not completely remove such heavy metals. So their removal is aided by addition of sulfide since most heavy metals are sulfide seekers. Further, electron deposition or the reduction of metal ions to metal by electrons of an electrode, reverse osmosis, and ion exchange are frequently employed for metal removal. In addition, solvent extraction using organic soluble chelating substances as well as activated carbon absorption is also effective in removing many metals. Next, for the removal of dissolved organics, usual methods for removal of dissolved organics material include adsorption on activated carbon, adsorbent synthetic polymers utilization, and oxidation of dissolved organics. Next, for the removal of herbicides. Um, Activated carbon treatment is the best means of removing herbicides and their metabolites from drinking water sources. However, a problem with activated carbon is that of preloading, in which natural organic matter in the water loads up the carbon and hinders uptake of pollutant organics such as herbicides. Thus, pre-treatment to remove such organic matter such as flocculation and precipitation of humic substances can significantly increase the efficacy of activated carbon for the removal of herbicides and other organics. Next, for the removal of dissolved inorganics. Membrane processes as the most cost-effective means of removing inorganic materials from water as compared to distillation and freezing. Membrane processes considered most promising for bulk removal of inorganics from water are electrodialysis, ion exchange, and reverse osmosis. First, electrodialysis consists of applying a direct current across a body of water separated into vertical layers by membranes alternately permeable to cations and anions. Then cations migrate toward the cathode and anions toward the anode. Eventually, cations and anions both enter one layer of water and both leave the adjacent layer. For ion exchange process, it is used for removal of inorganics consists of passing the water successively over a solid cation exchanger and a solid anion exchanger, which replace cations and anions by hydrogen ion and hydroxide ion respectively, so that each equivalent of salt is replaced by a mole of water. Lastly, reverse osmosis is also a very useful and well-developed technique for the purification of water. Basically, it consists of forcing pure water through a semi-permeable membrane that allows the passage of water but not of other material. Next, for the removal of phosphorus, um, phosphate is chemically most commonly removed by precipitation. In fact, precipitation processes are capable of at least 90 to 95% phosphorus removal at reasonable cost. Lime or calcium hydroxide is the chemical most commonly used for phosphorus removal. Additionally, phosphate can be removed from solution by adsorption on some solids, particularly activated alumina or simply aluminum oxide. With this method, removals of up to 99.9% of orthophosphate have been achieved. Lastly, for the nitrogen removal, nitrification followed by denitrification is arguably the most effective technique for the removal of nitrogen from wastewater. The first step is an essentially complete conversion of ammonia and organic nitrogen to nitrate under strongly aerobic conditions. Then the second step is the reduction of nitrate to nitrogen gas. This reaction is also bacterially catalyzed and requires a carbon source and a reducing agent such as methanol. Alright, I think I've already covered everything. That would be all, Miss Isa. Thank you for having me here.
What a technical yet enlightening topic, Mr. Gogolin. Thank you for that. Once again, Mr. 𝔼ℕ𝕍𝕀ℝ𝕆ℕ𝕄, Water Treatment Specialist of Maynilad Water Services Incorporated. Now, as much as we want to chat with our experts more, now we have to say goodbye to them as our time with them is only limited. Thank you once again to our experts. May you continue being environmental advocates of our country, and may we use your educational talk to be more environmentally known. Now, water treatment for certain purposes cannot be complete without discussing how it can be disinfected. As a resident environmentalist journalist on these topics, I will now be giving you a brief explanation about water disinfection. Now, based on my research, water disinfection or purification of water can also be done using 3 disinfectants, namely chlorine, chlorine dioxide, and ozone. First disinfectant, chlorine, is the most commonly used disinfectant employed for killing bacteria in water, especially in drinking water. It is employed to disinfect effluent from sewage treatment plants, as an additive to the water in electric power plant cooling towers, and to control microorganisms in food processing. Free available chlorine chemical species such as hypochlorous acid and the hypochlorite ion is very effective in killing bacteria. Chloramines, combined available chlorine, on the other hand, although a weaker disinfectant than free available chlorine, is more readily retained as a disinfectant throughout the water distribution system than the free available chlorine. However, while in the pipes it produces small amounts of chemicals, called disinfection byproducts, if the source of water has higher levels of dirt or germs, that may react with chlorine. And sometimes, there is not enough chlorine left to kill the germs in the water by the time it reaches the end of the pipes. For the second disinfectant, chlorine dioxide is an effective water disinfectant, which is a gas that is violently reactive with the organic matter and explosive when exposed to light. For these reactions, it is not shipped, but is generated on-site by processes such as the reaction of chlorine gas with solid sodium hypochlorite. Chlorine dioxide can be effectively used to disinfect drinking water without much alteration of palatability, and can also be used to destroy pathogenic microbes, including viruses, bacteria, and fungi from vegetables and fruits. Some studies even confirm that chlorine dioxide is effective against the resistant Mycobacterium, H1N1, and other influenza viruses. Lastly, ozone, known as a naturally occurring gas in Earth's atmosphere and is one of nature's most powerful oxidizers, is sometimes used as a disinfectant in place of chlorine. Basically, air is filtered, cooled, dried, and compressed before being exposed to a 20,000 volt electrical discharge. After that, The created ozone is pumped into a contact chamber when it comes into contact with water for 10 to 15 minutes. Ozone is a powerful oxidizing agent which, when dissolved in water, produces a broad-spectrum biocide that destroys all bacteria, viruses, and cysts. Furthermore, ozone is more destructive to viruses than is chlorine because it is capable of destroying all bacteria, algae, and biofilms within water systems, with no risk of resistance buildup or immunity. Aqueous ozone has a proven track record of readily and rapidly eliminating 99% of known viruses, including resistant and problematic aqueous microorganisms such as Giardia, Cryptosporidium, Streptococcus faecalis, and E. coli, all of which are renowned for causing grave human health concerns in potable water. Unfortunately, the solubility of ozone in water is relatively low, which limits its disinfective power. Indeed, together with me and the speakers, and hopefully the audience, we have learned a lot regarding water treatment, especially the ways on how it is decontaminated for various purposes such as basic things like drinking water. Alright, that concludes our educational talk. I hope the audience learned a lot in this special segment and special coverage of this show. Once again, I am 𝔼ℕ𝕍𝕀ℝ𝕆ℕ𝕄, your local DZES 143 radio host and resident environmentalist. Being the voices of nature for a greener future, delivering nothing but the truth. This is DZES 143 in your radio dial. Stay in the know by being environmentally know. Good day.